Hydrogen is often called the fuel of the future, and green hydrogen, the variety produced by splitting water with renewable electricity, sits at the center of that vision. But even as wind turbines spin and solar farms expand, the cost of green hydrogen remains stubbornly high compared to fossil-based alternatives. A significant portion of that cost comes from catalysts, the materials that accelerate the hydrogen and oxygen evolution reactions inside electrolyzers. Traditionally, platinum and iridium have done the heavy lifting. They are excellent at the job, but they are also rare and expensive. If a cheaper, abundant material could perform just as well, the economics of hydrogen could shift dramatically. This is where graphene enters the conversation. Graphene, a single layer of carbon atoms arranged in a honeycomb lattice, has exceptional properties: extraordinary electrical conductivity, immense surface area, and remarkable mechanical strength. Since its isolation in 2004, graphene has been hailed as a wonder material with potential applications across industries, from electronics to medicine. In the context of green hydrogen, its ability to conduct electricity efficiently and its tunable surface chemistry make it an attractive candidate as a catalyst or catalyst support. Over the last few years, researchers have published breakthroughs suggesting graphene could reduce costs by slashing precious metal use or by replacing it altogether. One of the most striking examples comes from a July 2025 study by the Dalian Institute of Chemical Physics. Researchers created what they described as a graphene chainmail catalyst by enclosing cobalt-nickel nanoalloys inside single layers of graphene. This design allowed electronic interactions between the graphene and metal alloy to optimize catalytic performance. By adding only trace amounts of platinum as single atoms, they achieved high current densities, up to 4 amps per square centimeter at just over 2 volts, while using far less platinum than standard catalysts. Stability tests showed the material could run for over 1,000 hours without significant degradation. Such performance at such low precious metal loading is precisely the kind of step change the hydrogen industry needs. In the United Kingdom, First Graphene partnered with the Center for Process Innovation to develop metal-oxide doped graphene electrodes. These electrodes reduced the extra voltage needed to drive the hydrogen reaction by almost half compared to commercial alternatives. At benchmark current densities, their overpotentials dropped from about 0.305 volts to roughly 0.175 volts. Reducing overpotential directly cuts the electricity required to produce each kilogram of hydrogen. Since electricity is the largest single cost in green hydrogen production, improvements like these translate into meaningful savings. The same study also reported improved throughput and stability, suggesting that graphene-based electrodes might extend the lifespan of electrolyzers while lowering operating costs. These laboratory results fit into a broader trend. Across journals and conferences, reviews of graphene-supported electrocatalysts show that manipulating graphene's defects, dopants, and interfaces with metal-sore oxides can tune its catalytic behavior. Doped graphene, where foreign atoms like nitrogen or phosphorus are introduced, can create active sites for hydrogen reactions. Graphene quantum dots, edge-rich graphene sheets, and hybrid composites have all shown promise. Computational studies predict that properly engineered graphene could rival traditional noble metal catalysts in some applications. However, it's important to remember that making green hydrogen cheap involves more than just improving catalysts. The levelized cost of hydrogen includes electricity prices, electrolyzer capital costs, balance of plant components, water purification, compression, and distribution. Catalysts influence some of these factors, particularly efficiency and stack cost, but cannot overcome high electricity prices or poor project design. Even the best catalyst will not make hydrogen cheap if the renewable power feeding it is expensive or intermittent. Still, catalysts are one of the few levers engineers can pull to reduce costs without waiting for policy changes or major infrastructure investments. A more efficient catalyst reduces energy waste, lowering the electricity input for each kilogram of hydrogen. A durable catalyst extends the life of the electrolyzer, spreading capital costs over more operating hours. And a catalyst that minimizes or eliminates the need for platinum or iridium can significantly reduce material costs. When these gains are combined, they can bring the overall hydrogen price closer to competitiveness with fossil-derived hydrogen or blue hydrogen made with carbon capture. Graphene's role in this is particularly compelling because it not only supports or replaces precious metals, but also enhances their performance. Encasing cobalt-nickel alloys in graphene, for example, prevents the alloy from degrading and optimizes its electronic structure, which means even tiny amounts of platinum are used more efficiently. Other studies have shown that graphene coatings can protect catalysts from corrosion, further extending their operational life. But scaling up remains a challenge. Producing high-quality graphene at industrial volumes with consistent defect density and doping levels is still expensive. The methods used in laboratories, chemical vapor deposition, mechanical exfoliation, are not easily or cheaply replicated on the ton scale. There are promising approaches such as liquid phase exfoliation or biomass-derived graphene, but these need to prove they can deliver the purity and structural control required for electrolysis catalysts. Durability under real-world conditions is another hurdle. Laboratory tests often use ultra-pure water, steady temperatures, and controlled currents. Industrial electrolyzers face fluctuating loads, contaminants in feed water, temperature swings, and start-stop cycles. Graphene-based catalysts must prove they can withstand these stresses for tens of thousands of hours. Even small losses in performance or structural integrity could erase cost savings if replacements or downtime are required. Additionally, catalysts are only one part of the electrolyzer. Membranes, seals, current collectors, and power electronics all contribute to cost and efficiency. Even a perfect graphene catalyst would not eliminate the need for improvements elsewhere in the system. To make hydrogen truly cheap, the entire electrolyzer design, from the membrane to the gas handling system, must evolve in tandem with catalyst technology. Still, the potential is undeniable. Industry analysts estimate that if catalysts can reduce overpotential by 20 to 30% and precious metal use by half or more, overall hydrogen production costs could drop by 10 to 20% in the near term. Coupled with falling renewable electricity prices and improved electrolyzer manufacturing, that could push green hydrogen closer to the $2 per kilogram target, often cited as the threshold for widespread adoption. In optimistic scenarios, where graphene production becomes cheap and standardized, and where single-atom catalysts supported on graphene achieve long-term stability, costs could fall even further. In such cases, green hydrogen could compete directly with fossil-based hydrogen in many regions without subsidies. That would open doors for hydrogen in sectors like steel making, ammonia production, shipping, and heavy transport, industries where direct electrification is difficult or impossible. The next few years will be crucial. Pilot plants using graphene-based catalysts must demonstrate their economics under real conditions. Manufacturers will need to scale graphene production without losing quality. Electrolyzer designers will have to integrate these catalysts into systems that maximize their benefits. Policymakers and investors will watch these developments closely to see whether graphene can deliver on its promise. Even if graphene does not single-handedly make green hydrogen cheap everywhere, its influence is already reshaping the research landscape. By proving that performance can be achieved with less platinum or iridium, graphene catalysts are forcing a rethinking of how electrolyzers are built. They are inspiring hybrid designs that combine abundant base metals with graphene supports, reducing dependence on vulnerable supply chains. And they are demonstrating that the green hydrogen sector can innovate its way past some of its toughest barriers. The story of graphene and green hydrogen is, in many ways, the story of the clean energy transition itself, a sequence of small, technical improvements that, taken together, create a seismic shift. Streetlights powered by hydrogen at a small port, buses refueling at dawn in a California depot, offshore turbines feeding electrolyzers in Rotterdam, each is a small event. Yet over time, these events accumulate into a transformation. Graphene catalysts might not be the final piece of the puzzle, but they are clearly one of the most promising. If they succeed, future generations may look back on papers describing graphene chainmail or doped graphene electrodes as the quiet turning points that made hydrogen affordable. They may not remember the exact voltages or current densities, but they will live in a world where clean hydrogen is common, not costly. The transition will not happen overnight. But like so many revolutions in technology, its most important steps may be the ones taken quietly, in labs, in pilot plants, and in the thin carbon lattices of graphene sheets. Graphene catalysts, then, are not a silver bullet but a significant lever. Their promise lies not only in their extraordinary properties, but in the way they enable other pieces of the green hydrogen puzzle to fit together more easily. They extend the usefulness of precious metals, lower electricity consumption, and hint at pathways toward durable, affordable electrolyzers. Whether they will finally make green hydrogen cheap depends on scaling, integration, and persistence. But the evidence so far suggests that the answer could be yes. If not everywhere and all at once, then gradually in more and more places, until clean hydrogen becomes an unremarkable part of daily life. Call to action. If these developments excite your imagination or spark ideas for your own projects, dive deeper into the world of green hydrogen innovation at EH2 Hub. ReneEnergy.com. Explore feasibility tools, financial models, and expert networks designed to help you understand, plan, and participate in the clean hydrogen future. Share this video or article with colleagues and friends interested in energy technology. Together, even small conversations can accelerate big change.